it's gotten much worse since then. That's so. I thought I would continue for some reason to say something about controls topics instead of optics, because I just I guess I would just amplify what Peter says. I think it's much more what he said plus times 100 is the I think we have a lot of interesting controls problems which we are handling, but the amount of, if you look at the amount of sophistication that exists already in something like quantum noise handling or design of the mechanical system, those things are pretty far along, and with a lot of effort we're in the game of getting 10% or something like that. But that's not the case with the control system design, and the amount of open projects which are left, which can give us big advances in sensitivity, are huge. I mean, of places where you could work and make a big impact, I would say the controls area in this field is it. So there's so many things to talk about. I thought today I would talk kind of give a survey of what are some features of what's going on in terms of feedback controls in this field. And so just to say something like here are, and Peter's already described how the basics works. I just wanted to give some examples and say here are a couple of interesting problems we've had to solve, and here's why maybe there's more to be done on it. I would say so. Yeah, let me just go. So what Peter's described to you so far is the single input, single output system, and in a lot, in many cases, what we are dealing with instead is a thing that has multiple inputs and one output, multiple single inputs and multiple output, or truly complicated ones that are multi-input, multi-output. And the jargon for all of these is CISO, single input, single output. For what you've just seen, there's MISO. We have this multiple sensors for a single system. We do that quite a bit. Single input, multiple output. I think we don't have any of these. Let's cross it out. And then it's gotten to the case where we now have true MIMO operation going on in the operation of our seismic isolation systems, suspension systems, and then also the optomechanical system, which is the interferometer. And I don't have it written down here, but let's try to just think about the complexity which is in this system now. So we have these. We'll just work our way up from the ground. So we have first of all these seismic systems which we talked about. There was this drawing. We have this pillar and a thing inside, and on each leg we have a system, and then inside of here we have a table like this, and then suspended from the table is another table, and then suspensions. So how many feedback systems do we have operating here? For these chambers, we have 4 legs, and each leg has 2 degrees of freedom. It has 1 horizontal and 1 vertical. So let's say for this hydraulic system, we have let's say 2 times 4 per chamber. So one horizontal, 1 vertical, and then 4 legs. Then we have these tables. These tables have let's break it out so we can really see it. These tables are done by having a pod sort of system on each end, and each one of these has a vertical sensor, which I'll draw this way, and then a horizontal sensor like this. And then each of those sensors in turn is a hybrid sensor system built up of a low frequency sensor, which is the position sensor I referred to yesterday, plus then a medium frequency inertial sensor, and then a high frequency inertial sensor. So each one of these arrows can be 2 to 3, depending upon which stage I'm talking about. Let's just say 2. So we have 2 times 2 here, and then 3 corners times 3. So there's 12. So we have 12 sensors per table and 2 tables, so 24. And so that's giving us 24 plus 8. So that's 32 sensors per chamber. And then we've got 4 chambers, 2 chambers for each arm cavity, 2 arm cavities, and then a few more in the central station. Let's say something like 7 chambers, roughly. So it's 32 times 7. So we're now at 210 seismic sensors. This is already a lot. I think this diagram that Peter showed you to impress you about how complicated our feedback system is not the other way. It would lull you into a false sense of simplicity. It's nowhere near that simple. This is just seismic systems, and these are somewhat acting independently. You know, I can turn on these feedback loops, and then sit around for a little while, and then turn on these feedback loops, and then turn on these feedback loops, and this, more or less, the action of this thing doesn't shake this one too much, and it doesn't turn this into a 210 by 210 matrix, although, you know, completely formally it would, you know, and in some, if you're really a detail-oriented person, you have to think that if I push this pier 4 kilometers away, there's going to be an acoustic wave that travels through the ground and interacts. But we're sane people, so we don't consider terms like that. But even so, there's going to be some cross-coupling within the system. It's not this big, but this is starting to get to be a tough MIMO problem. Certainly, in each of these stages where you have a triangular stiff body, at the very least you have to control the 6 rigid body degrees of freedom, and then once you get to high frequencies, as Peter was saying, you have to start to think about these internal resonances of the system. It's no longer a rigid body. So it's quite a lot of degrees of freedom you have to control. But the advantage, you have 2 advantages. One is they're somewhat decoupled by careful engineering, and 2, there's no kind of real bootstrapping problem. The sensors are on all the time in some sense. There's no bootstrapping like we have for cavity designs, where first you have to get the cavity locked in order to have an error signal in order to lock the cavity. There's no nutty logic like that. The sensor is just there. You can turn on the gain slowly and make the system work. Okay, so that's there. A lot of sensors, so that's a scary number of sensors, but somewhat tractable. Let's see. I won't go through the same issue with the suspension. It's not such a tough controls problem. There's a lot of degrees of freedom which have to be pushed around, which make it so that the A block that Peter had, the actuator block, is a kind of complicated thing in the Laplace domain, and there's a lot of degrees of freedom to control. But it's in itself is not a very complicated MIMO problem. Let's look at the optical plant that we have to control. This is the first of the most challenging problems that I think we have. So this, if you think about just the optics and not the complicated suspension, the system looks like this. So I'm putting a little bit more complexity than we usually put into it, just to show you the annoyance of it. L. I know it's starting to look like I'm drawing a ridiculous number of optics, but I'm very carefully leaving out many of them just so that it's a simplified diagram. But I wanted to draw here at least all of the actual cavities that we have. Something like this. Okay. More or less, this is what it looks like. There's two arm cavities, this sort of short Michelson thing. These things, which I'm going to tell you about tomorrow, the power recycling cavity and the signal extraction cavity. It's the name I want to start calling it now. Yeah. So what are the number of degrees of freedom we have to control if we just consider the longitudinal motion? We have 1, 2, this one, let's call this S, and then some sort of differential length here, minus like that. So within the main interferometer, there's 5 degrees of freedom to control. We also have this degree of freedom, let's say, input mode cleaner, perhaps a laser wavelength, and then over here we have this other little cavity just before the, maybe we've never drawn this before we actually do the GW readout here. So somehow all of these have to be controlled. And what's the difficulty in any of these systems? Well, in the seismic control system, we had our predefined sensors, and there was the problem was one of how do we merge together all of these sensors so as to produce low enough noise readouts, and then make some sort of stable feedback, and sort of pre-isolate this system so that the displacement noise is low enough. In this case, what we have to do is say, this is a complicated system. All of these fields are bouncing around in here, and until yesterday, we didn't even know about this matrix technique. How are we going to read out all of these signals and make some use of it? We find out, in fact, as we try to read out, let's say we take pick off from here, and we'll get a pick off from the power recycling cavity. We can also take the light which is reflected out this way. We can read it at a few places, let's say, and you can imagine reading at a couple of places. But without going through the calculation, you can see what one of the serious problems is here. Any place that you stick your photodetector, because this is a complex resonant system, the field which comes out is going to have some contribution from all of the other mirrors, unless you've carefully somehow arranged for some cancellation, which makes this kind of painful. If you say, well, I'd like to figure out what kind of force should I apply to this thing. Yeah. How would I possibly figure that out? You read out 5 or 6 photodetectors, and you have to do something. You have to control this thing so we don't get into this nonlinear regime we talked about. Are there any thoughts? You don't have to be right. You just have to guess.
I just wanted to ask, all those pick-off points, you keep the photodiodes, are they controlling the local place, or do they have a overall?
Right, exactly. But what we would hope is that it could be what you're saying, and that if you put a photodetector close to this mirror, then it would mostly be reading out the signal from this place. But unfortunately, the way that we've designed the system basically to have a strong transduction of gravitational wave strain to this detector, and also try to make it sort of immune to noise sources. And by making this design choice, as it turns out, none of these things are very separate from each other. So this one, you may say, what's the fraction? How sensitive is it to the motion of this mirror as opposed to this one or this one? And it's not very well separated. It more or less has. It's not really equal contributions. It's mostly seeing the signal from the longest cavities, but it's not preferentially seeing this one over this one or this one over that one. It has some admixture of all of these. And so what we have to do is say, what we'd like to do is get an independent readout of these degrees of freedom, and we can say the common mode distance of the arms, the differential arms, and then these three short ones, the power recycling cavity, the signal extraction cavity, and the Michelson length. And then there's a matrix which we don't know, and over here we can list something like we have these vector of signals. So we have the time series from all of these things, and somehow we'd like to form a matrix to reconstruct what are the fluctuations of all of these degrees of freedom. Okay, so that seems reasonable. It seems like if we have a good optical simulation software, we should be able to do it. And this afternoon, some of us started trying to use optical simulation software. There's some headaches there, but in principle, it can be done. As it turns out, though, this matrix is not constant because you have different time constants to all of these cavities. And so all these matrix elements, in general, have to be frequency dependent. And you can make some approximations there, of course, and say, I don't care about the time constants associated with short cavities or something like that. But more roughly, this is the problem that exists in order to control just the longitudinal degrees of freedom of the system. Okay. Yeah, I'm not giving you any answers there. I'm kind of complaining and just saying it's difficult.
This is the sensors, but what about the actuators? Are they also similarly cross-linked?
Yeah, a little, but it's not too bad. It's not too bad. Yeah, Suresh's point is a good one. I was going to ignore it because it's sort of complicated, but it's true. Because we plan to operate the system at high power, it becomes the case that if you shake this mirror over here, all of these other ones move a little bit too, just because the effect of the pushing one via radiation pressure applies some force to all of the other ones. But we're not in such a crazy regime that you have to really, really pay attention to that. You sort of do, but for this problem of controlling the length of all of the cavities, it's not necessary. No, it's not correct to say it's not necessary, but if you forget about it, then it's still okay. I don't know what to, yeah. You know what I mean. I mean, I forgot about it, and, I'm still okay. Let me now erase a few of these things, but not the whole drawing. My opinion, maybe the hardest controls problem we have is the next higher order thing, which is the control of the angular degrees of freedom of the system. And this is a problem that was so tough it almost at each stage of the LIGO project, it's almost kind of been the downfall. That we tried to figure out how to control. It seems simple. We just sort of, point this mirror down this way. Right? Simple enough, and anyone can do this. You take something like a laser pointer and point it at your mirror, and when the mirror moves, the beam coming back moves, and you can detect it with some sort of position sensor, and job is done. Right? Yes. But there are challenges. In addition to the fact that you have to control all of these degrees of freedom, and this matrix business that I just talked about exists. Of course, that's there. So there's a lot of cross-coupling, but qualitatively, that's only as difficult as this length control problem. So let's say you've been able to solve it for this single degree of freedom. Perhaps that means you can understand this matrix for the angles as well. For the length sensing, of course, we have the problem that we're trying to achieve this sensitivity of 10 to the minus 19, 20, 21 meters per square root of hertz. And so it means the sensors have to be very exquisitely good, and we have to be careful when doing the actuation that we don't take some noisy signal over here and use it to feed back onto the very precious test masses and spoil the sensitivity. So there's some care has to be taken about how one allocates the feedback in that way. And so it turns it into a pretty complicated simulation problem. Okay, that's fine, but that's just a problem, sort of several degrees of freedom. When you get now to the angles, the problem is quite different. So now now it's no longer the case that you have sensors which are so good. Let's try to think from this. Let me come back to it. I have one thing about controls I'd like to tell you first. I'll skip ahead and just say the punchline for why the alignment controls are so difficult is because we're sort of lacking angular sensors which are good enough, which would allow us to have the capability to have enough feedback and do so without spoiling the sensitivity. But I should draw a diagram of feedback loop with noise before I get to that. Yes. So I'm just going to draw a more simple version of the diagram that Peter had just a second ago. And sorry for changing all the variable names. But anyway, it's not so complicated. You can see what to do. So this is the same thing as was there before. And here I'm trying to show sort of what things would look like when we try to control something like a Fabry-Perot cavity. So here our plant includes both the dynamics of the actuator, perhaps a pendulum, and then also the frequency response of the optical cavity. So it's some sort of mechanical resonances and then, let's say, a single pole. And this H is our feedback system. So it's whatever analog or digital controller we put onto it. And U is our control signal. E is our error signal. And then the thing that I've added here is the presence of noise. So in an optical cavity sensing, here, just before the error point, we can add in shot noise, N sub S. And also we have some sort of force noise. So let's say we're trying to do our experiment and somebody's coming by and shaking the cavity or for some reason. So what we can write down now that we know how to do the algebra is what are the influence of these noise sources on the actual degree of freedom which we want to be small, which is this, let's say. So let's say X is by our control system, we want our overall system to be our variable X to be small. So how do we do it? So we'd like to calculate. Let's start with force noise and say we inject a force here. How does it show up here at X? There's some whispering. E? Yeah, P times, okay, so P times force gives us how this noise propagates to here. But what about the effect of this feedback loop? You've just seen it like a few minutes ago. It's yeah, that's right. So as always is the case, if you stick in a signal and you look immediately after you've added this signal, if we look right here, this point is going to be n sub f divided by 1, and I put minus because that's I am. But it's whenever you put in a signal, right after you've put in the signal is suppressed by this 1 over 1 minus g, the overall loop gain, HP. And then once we have the signal here, it's easy to propagate it to here, right? Then we just multiply by p. So we can say x is equal to n sub f over 1 minus HP times p. So simple enough. And by the same logic, we can also do the propagation of n sub s, right? So n sub s going to E is going to have the same thing, 1 over 1 minus HP, and then it gets multiplied by H and by P before it shows up at X. So X is also going to be equal to n sub s over 1 minus HP times HP. Right? Right. So, why am I telling you about this? Yeah. So this tells us how we can calculate the propagation of both shot noise and force noises to any point basically in the system. So let's go back to this story I was telling you here. So in this case, here's our gravitational wave readout, and we have somehow sensors all over the system which are feeding back torque to all of these optics. And our question is, how good do we have to do? How much do we have to suppress the motion of the angular motion of these optics, so as to not erode our gravitational wave sensitivity? Right? And well, I mean, easily you can see. Let's say this is our mirror, and if the laser beam is hitting here and coming back, if I rotate right around this central point, there's in fact no effect. Angular motion of the mirror has no effect on the longitudinal phase shift of the beam, and thereby there's no requirement at all. Are we going to let the angular modes of the mirror swing all over the place? And then your response should be, pah, totally false. No? Why do you think this is totally wrong? I'm saying, in this picture, I have the beam coming to the center of the optic and coming back. And so I'm saying, if that's the case, then this funny other degree, mostly we're concerned with how much the cavity lengths are changing, because this is the degree of freedom which shows up in our strain readout. Right? And so I'm saying, if this is going on, I'm talking about, for some reason, control of the angles of the optics. Why does control of the angle of the optics matter for a strain readout? I'm telling you, just a few minutes ago I was saying this is such an important controls problem, but then I'm saying it's not important because there's no cross-coupling between these degrees of freedom, so who cares? You said?
Gets coupled to the length.
Yes, it must, right? But how?
Finite.
Hmm?
Finite size of the beam.
No.
When the total length the beam travels increase or change.
Yeah, but if it's rotating right around the central point, then that's not the case. Yeah, I mean, the answer is that it's not rotating around the central point. Any time in this field anybody tells you that this thing perfectly cancels because such and such thing is 0, you can just note that down as a place where there's going to be trouble, because someone has imagined that something is going to be 0 and it's not 0. So all these things are moving around, and there's going to be some fluctuation here. And in practice, the RMS fluctuation is around a millimeter. And for a beam this big, and it's moving by a millimeter, and you can kind of easily see for yourself from geometric arguments, if the beam moves by a millimeter, then the coupling from angle to length will be 1/1000. So 1 nanoradian of tilt will look like 1 picometer of length shift. And remember, we're going for, let's say, 10 to the minus 19 meters. So 10 to the minus 19 meters divided by 10 to the minus 3 meters is equal to 10 to the minus 16 radians. Seems like this whole project is doomed. 10 to the minus 16 radians. How can you ever measure something like that? It's not likely. I think you can use high power lasers and do long arm quadrant sensing and enormous effort can get to the level of something like 10 to the minus 12 radians. And I challenge you to even make something that good. It's like a whole year of my life to make 10 to the minus 12. And I thought it was pretty good.
Yeah, it's tough.
Today morning, Solson showed the traces from R.V. Jones' paper.
Who's Jones?
The guy who did the torsion balance thing in different.
And
What did he have?
he constructed a optical lever 10 to the minus 12 radian, maybe about, 60, 70 years ago.
How long did it
3
take?
years ago, I don't know. These are some continuation of those kind of investigations. Jones and Richards, I think that paper.
Okay, so in 1 year as a grad student, I matched Jones. And then after several more years, the entire LIGO project has achieved, in fact, a sensor of 10 to the minus 15 radians. So we're getting there, but anyway, we still don't have 10 to the minus 16. 10 to the minus 16 is still a challenge for us. And so anyway, the reason I'm telling you about these two things is that basically the problem is we have to control the motion of these mirrors down at low frequencies where things are going on, like these microseismic fluctuations I was telling you about, plus there's the whole range of optomechanical instabilities I'm not telling you about. So basically below 1 hertz we have to have some strong control. And by 10 hertz we have to achieve this goal of not introducing more than 10 to the minus 16 radians. If we introduce 10 to the minus 16 radians, that means that the angular noise we're injecting is equal to the quantum noise. So the whole point of having good quantum noise is already ruined. It means there's no hope of doing squeezing or things like that because of this annoying technical point. And so what this controls problem entails is how do we get this strong control at 1 hertz and then using this kind of algebra, using the noise propagation, figure out how do we achieve this or a little bit smaller. And the trick is in this. So this is the term I'm talking about, that we somehow want to make this term small. And P is just what it is. We have no control over that. That's just the mechanics of the suspension. What we have control over is this H term. And that's a little bit what Peter was saying was possible and impossible. That what we'd like to do is have a system that has, I'm not sure what I'm plotting here, like this, that has a huge gain at low frequencies, and then maybe here around 2 hertz or something crosses over, and then by the time it gets to 10 hertz has some, almost zero gain. Yeah.
Noise comes in, right?
Yeah, exactly. So in this region down here where HP will be much larger than 1, the best you can do here is stabilize to NS. So I guess it's lucky for us we're not trying to detect anything down there because we can't do better than this limit. But up here at high frequencies, this is the real challenge. And so what we need to do is somehow design some very exquisite filter which has doesn't give rise to too much instability here in the real control band and really rolls off the noise quite a bit by 10 hertz. And it's we need more, we need more work, we need more brains, we're going to need some help to figure this problem out. And it may be solved by the time the interferometer comes to India, maybe not. So don't expect it to show up perfect. Anyway, the whole work here is in designing P. But how do we actually do this problem? You know, you can't. You know, if you have one servo you need to control and that's it, then surely you can spend all of your days just soldering things in and changing the size of this capacitor and doing that other thing and working on the shape of this thing until you ultimately you get something. But this is no way to live. This is one loop out of hundreds and hundreds that we have. And some of them are easy, but there's a lot of them which have this complication. I mean, this thing, when you draw it in the Laplace domain, is going to be something like, it's like a 40th order polynomial. It's not any kind of simple structure. But there is a solution, which I'll tell you about tomorrow. But it's what I'm trying to say is we're getting to the regime where we need to use larger scale methods than what we've been doing so far. The concept of one clever physicist sitting there with 2 soldering irons and a bunch of wires or something it's not even 20th century. It's a prehistory kind of thing. Do I have any time left? Am I getting into Ollie's time? Yeah? Okay. So there are a couple topics I hope to tell you about tomorrow, which is, I would describe the Statespace stuff because Statespace, the Soviets really got onto this in the 50s or 60s, and Americans caught up to them after some 10 or 15 years, and people in LIGO are getting into it sometime in the 21st century. So we're catching up to this. There's a really good book on Introduction to Statespace Methods by Friedland, I think is his name. It's a Dover book. It only costs $5 or $6. But the book is aimed at if you are a poles and zeros transfer function kind of guy and you'd like to learn how to use Statespace, this is the book for you. He takes 50 pages to explain the basics of it. It's very good. But in the modern times, people use more sort of optimal and adaptive techniques where they define some sort of cost function for what they want, rather than sit around and look at plots and say, that's not so good. They just write down a formula for what needs to be done and then construct a controller, which I can describe tomorrow. But for today, I wanted to make a comment to what this thing that Ollie showed. He showed this dual loop intensity servo. And so far we've just showed you algebra about single loop, right? And that seems okay, single loop, you know, a few slides and some diagram. But how are you going to do the algebra for 2 loops? Well, I mean, you could go through the same exercise of trying to do just some diagrams and make things go around, and it's kind of by hand construction. But things are getting much worse. And if you're trying to control a 6 degree of freedom system, you're going to have 6 loops, at least, which are all interacting and have cross-couple terms. And you draw this loop, but draw 6 loops, and then have connections at some point between all of these loops. And no way can you do it. I've gone through the exercise of doing it that way for 2 loops, and that was something like a few pages of algebra, and it's kind of incomprehensible a few days after I've done it. So what we need is a technique to do it more reasonably, and I will show you. So I'll draw this 1 loop, 2 loop thing that Ollie was showing you, but with vast simplifications. So this is the 1 loop. There's a filter. The filter goes to AOM, which let's say is flat. It has no transfer function at all. And then this line represents the transmission of that AOM, and that it goes through the let's say pre-mode cleaner. And let's say also that's flat. And then there's a photodetector there, and you look at that signal. So this is roughly the loop. And you have this thing which is flat, this thing which is flat. So your task is just to make, when you have a plant which is flat, all you have to do is make a controller which has, a controller which by itself is stable. So this is a really, really easy loop design problem. Okay. However, it's more complicated than that when you add the second loop, right? So the laser light, which is transmitted from this AOM, goes into this next thing, which is the suspended input mode cleaner. And this actually has something. This has a corner frequency of around 8 kilohertz because it's such a long cavity. And then the transmission from this, this goes to a photodetector. The output of that comes into the second piece of control electronics, H2, and then this comes back and sums into the error point of this thing. So this is about as simple as a double loop thing as we can draw, I think. So any thoughts? And as a hint, I've already told you the answer earlier this week. That's a very good hint, isn't it? All right. I will give you as much time as it takes me to plug in the video to my laptop. There should be some sort of countdown.
Single frequency.
Say it louder.
Single frequency response we can transfer.
You're saying how to measure it. Yeah.
Algebraic solution for this. For a single frequency, we can calculate the algebraic.
Yeah. But I'm asking, how do you calculate the algebraic transfer function?
By Mason's gain formula.
Machine?
Mason's gain formula. Mason's gain.
Machines?
Mason's gain formula.
I'm not understanding.
Mason gains formula is there now to calculate the loop transfer functions from node to node.
Yes. Matrix gain.
Mason's gain.
What are you? I don't understand the word you're saying. Mason?
There's a formula called formula by George Mason.
Mason.
Yes. So he has this block diagram simplification. That's the formula.
Maybe I should learn this technique. Yeah, you should tell me about it after, so I can learn this thing. As it turns out, you can do just this matrix thing that I was telling you about before. So here, this is the 3x3 matrix, which represents the one loop. So how do I label that? I say, let's say this point is 1, and let's say, I don't know, this point is 2, and this point is 3. Like that. Then this, this first column tells you what's 1 to 2. That's this H1, and then 2 to 3 has a 1. So this point just goes to here with straight transfer function. 3 to 1, it just goes through the summing nodes, and it's also a 1. And everything else is 0, just like what we saw before. And so we can do the same operation as before. We do 1 over 1 minus this factor, and we get this thing, right? And this is basically telling us for almost all points, the transfer function is just 1 over 1 minus h, which is the controller in this case. So if we want to say, I put in a signal here, and what's the signal at 2? 1 to 2, that's going to be this h over 1 minus h. So it's the usual 1 minus h factor, and then you multiply by h. And so that's kind of the same thing we were saying here. You have the usual thing in the denominator for the loop feedback, and then you have the forward loop gain. And that's just sort of what this is telling us. So this result is a little bit trivial. We could have done it without a matrix, right? But it's good to see this just to make us happy that our previous algebra tool gives us the same answer. So now we can do some more labeling, and how do I put my labels? 4 and 5. So I labeled this as 0.4, the thing after the input mode cleaner, and then this output of the 2-loop controller as 0.5. And we can do it again. So you can see here, 1 to 2 is H1, and all the usual things for 1 to 3. But we have a couple of new terms. We have this 2 goes to 4, sees the M, the IMC mode cleaner transfer function, that's there. And 2 goes to 3 is there. And then the other non-zero element is this one, 4 to 5 is H2. And 5 goes to 1, here's a 1. Right? Okay, so that's all there. So it's almost no more trouble to write that down than it was for the 3 by 3. And then we can do the same thing again. And my screen is shrunk. Yep. Yeah, so for a pretty minimal amount of typing and then some stuff in Mathematica, we get all of the node-to-node transfer functions in the feedback loop that we wanted. And you can try to do that by hand without this technique by just doing the usual algebra, and you could get it. I think with enough pain you could get it. I think this is much less error-prone because it's pretty easy to write down each of these single-hop transfer functions, and then invert it to get this thing is quite nice. And for 2-loop, it kind of pays off, and it really, really pays off once you have three loops going on. So 3 sensors, 1 actuator, or 3 sensors, 2 actuator, any combination of these things. This thing scales pretty easily. All you have to do is accurately draw this kind of diagram, and then follow it around and make sure you haven't messed up the drawing. And the handy thing now is you can do you can do the sophisticated things you'd like to do, like say, well, my double loop intensity servo is underperforming. It's a factor of 2 worse in some band. Where could that come from? Well, you can easily just stick in all of the possible noise sources you can think of. This pre-mode cleaner is shaking, this angular jitter, some shot noise in this sensor, shot noise in this sensor, and scattered light noise. And you easily find the transfer function that takes you from this node to the place that you're making your measurement. It's a simple way to scale. And it works this way for 2. It works I think, anyway, it works this way for several loops. But it's a handy way to do algebra. Of course, you can also do all of this using some more professional software like Simulink and things like that for MATLAB. But this is handy because it gives you, without using any of those things, you get the analytic representation for all of these that you wanted to have. I feel like I'm much more excited about this matrix technique than anybody else. That's okay. That's okay.
Of the noise that we suspect exists.
Oh yeah, but there's no complication to that. That's just the NF, NS, whatever terms in there. Those just, it's just a single thing out in the front that you multiply this term by. But it's somewhat of a challenge, but it's not.
We need to guess or need to know their frequency dependence. Is that right, or can we reduce that in any way from our computations here? Do we need to know that a priori?
I think if I told you something different, you wouldn't believe me.
Yes, indeed.
Yeah, of course. Garbage in, garbage out, man. You put in the wrong thing, you're going to get the wrong thing.
No, but so if we are trying to guess at a noise source, and we already need to know the noise source, there is a problem. So
Yeah. I guess what this does for you is, in the case where your control system has quite a complicated loop shape, and you see a funny shape in your system, these things like shock noise or acceleration noises, are not actually complicated. They're sort of smooth power law things. And through the complication of the loop, they may look complicated. So by undoing the loop, yeah, you may be able to get it that way. But I think mainly it's neat because it has predictive power. When you're designing a system, you can do this. And you can use these tools like this Bayesian experimental design to optimize your system by adjusting parameters and minimizing some sort of thing that you want to do. Okay, that's all I have, and then I can answer questions about more specific feedback if people want to know.
One, how do you take care of back action? I mean, let's say you all the way assume that a block affects in the forward direction. How do you introduce loops in this formalism?
Let's see, what would be a piece of back action here? Well, I could make up something crazy and say, for example, the amount of stored power within this device, somehow a piece of light scatters over here and shows up here. Just, it's a spurious path. But I add a spurious path. And so I just put in a matrix element which goes from 4 to 3. Just make this something small, epsilon. And I don't have to work out the whole algebra for the thing again. I can stick in any spurious thing I want.
And the second question is how quickly the complexity of these matrices increase. I mean,
Yeah.
you have got lots and lots of control loops.
Yeah, I mean, definitely this thing increases a lot, but this seed matrix, the open loop gain matrix, is still simple in any case. And there's no reason, I mean, here I'm doing it analytically because I think it's nice to see how it's done, but in reality, when I have a super high order control loop, I would do the whole thing numerically. And then I would never display this matrix. I just use it to make the single point-to-point prediction that I would like to have. Just as we do when we do the optics simulation. The simulation gives us all of the node-to-node effects, but this is what I like to have. And I think this is another piece of development that one can do for finesse, probably, if people are looking to do the contribution. I think it's suggestive that you can use this matrix technique for feedback as well as optics. And it would be handy to be able to put in arbitrarily complex feedback systems into these optical simulation tools.
I have two questions. Active feedback reduces the effect of noise or a signal by the open loop gain by 1 minus HP factor. How does it retain the signal to noise integrity?
Yeah, I thought this was something that Peter was going to talk about, but it's. I was trying to estimate. I was trying to make a, in economy of slides, I wanted to try to predict everything he was going to say ahead of time, but can't be right on. Yeah, I think this is related to the question of something like if your gravity wave detector has a feedback loop bandwidth of something like 1 kilohertz, how can you detect gravity waves at 10 hertz? Seems a little bit troubling, right? Bala's worried. I mean, what if we're just canceling out the gravity waves all the time? And maybe we've made detections like 20 years ago and we're just like fools. Yeah. That would be very embarrassing. Let's say it shows up like this. Let's pretend it's showing up in NF. And then I, for some reason, just erased everything. So then, let's say we're doing our measurement here at E. So we'd like to say something like, how does NF show up at E? So we want to write down, again, NF over 1 minus HP, and then it gets multiplied by P. Yeah. So E over NF will be P over 1 minus HP. Okay. All right, that tells us about signal. And then the noise is maybe shot noise in this case. Yeah, so this one. So what's E over NS? This in NS at this point will also be 1 minus HP, and that's it, I guess. So E over NS is equal to 1 minus HP. So in this case, we're saying something like NF is our signal, right? And so the question is now, what's our signal to noise ratio? How should we define signal to noise ratio? NF by NS, yeah. I can never do this algebra, so someone has to make sure I don't get this wrong. E over P times 1 minus HP, and NS is equal to E 1 minus HP. So signal to noise is signal over noise. So this divided by this gives me 1 over P. So with this came out of it. H is gone. Yeah. Yeah. In this case, P is plant, because the people who did controls used to worry about their chemical plant. And they were the first people. But in this case, plant is mechanical suspension and also cavity.
The second question is that once the noise gets reduced by the 1 minus HP factor, how does it compare with the Johnson noise in the system?
Johnson noise. Ooh.
Because the noise ultimately will be measured by some resistor or some device which will itself have a noise.
Yeah.
So will it be higher than that or lower than that?
That noise also is suppressed by the loop. Yeah, I understand your question. I used to ask the same question. So you're saying something like, yes, this is shot noise, but right here there's some photodetector, like photoelectron turns to voltage, so there's some resistor R, and this has its own noise, right? Yeah. So this you can represent it as here noise Johnson gets injected, but Johnson noise will also be here. It'll be 1 over 1 minus HP factor, and eventually what happens is our system, where you measure it. Of course, there's some other noise, but we happen to do this measurement inside of a digital system where the floating point precision noise is not it's extremely below everything. Yeah, almost always. Yeah. So it's nice, and what we would like to have is have HP be as big as possible, because then our system is kept incredibly linear, and it doesn't seem to disturb anything. We hope that works.
I was just curious to ask about this interaction between the suspension and the cavity, but now it is clear that the plant represents both the suspension and the cavity controls.
Yeah, in this one I could separate it. Yeah.
But so that also is a localized control, because especially when you take say angular stabilization, so that will involve the mirror stabilization as well as the suspension. So
in this one I was trying to say something like, this is how we control the length of a long Fabry-Perot cavity, but you're asking something like, how does it work that we have local things as well as this global thing?
that's right.
Yeah. Yes.
This.
It's like this. So ignore the variables for the moment, but this is something like the local control, and this is like the global control. So this is the local thing which keeps the using some sensors nearby the suspension keeps the system from shaking a lot or that sort of thing. And this is the feedback which comes from the main multi-kilometer away sensors. So after everything is roughly controlled by this local system, this more global thing sends some feedback in and drives it in. And so they don't really fight. It's just you have to know that there's multi-loops acting and then calculate it the right way.
So that means the cavity and the suspensions are taken care of with this.
Yeah, exactly. We designed this local system so that it has a sensible transfer function that's easy for us to understand and doesn't have some very high Q resonances or something like that. It's easy to model and very smooth, and then it's more easy to design this H2 loop.
I know we are observing in the frequency band of 10 Hz to 10,000 Hz somewhere, but feedback always comes at some time t plus delta t. The delta t time it requires to go through the feedback system.
Yes.
Is it giving any problems?
Yes.
Yes. So now, then how to tackle them?
How to tackle it? Yeah, there's one problem which is to do with the round trip time of the light. So we use the digital control system, and the signal is sent to the end using optical fiber. And the delay is always going to be a little bit more than the light travel time. Maybe it's 15 microseconds or so. The delays which we get in any of the analog systems are not comparable to kind of nanoseconds or something. It's not important. The biggest delay by far that we see is because of the clock cycle time of the digital system. So this travel time is some tens of microseconds, but because we use computers which are, the real-time control is running at 16 or 32 kilohertz. If we have a few cycles of delay, then the biggest effect is that we have some 50 or 100 microseconds from the digital control system. But then you can say to yourself something like, if I have a sine wave like this, and then I want to make the anti-sine wave like that, and it's perfect, and I delay it by 100 microseconds. This thing, has a period at 100 hertz, tau is equal to 10 milliseconds, and so then you can draw this phasor diagram to see what's going on. Let's say this is the main signal, and what I'm putting in is exactly the cancellation effect, but there's this rotation angle that I have in the phase. And this rotation angle is going to be this 100 microseconds divided by 10 milliseconds. So it's something like 1 over 100. So this angle would just be 0.5 degrees. And so what's left from this phasor is this small residual in this direction. So that's kind of roughly the limit of what you can. But this is not a problem for us because it means that we can only achieve the suppression at 100 at 100 hertz, but we're only trying to achieve the suppression at something 4 or 5. One day, if computers are faster, then it's possible that our bandwidth